Great. So I'd like to thank the organizers for inviting me to give this talk, and also for allowing me to give it remotely in the interest of carbon. And I know that one of the best things about conferences is the coffee breaks. So over the remainder of the conference, I'm available for coffee breaks or dinner. Just drop me an email, and I'm happy to Skype at any time over a cup of coffee and discuss anything. Also, Carlo Spiracchieri is there. He's one of the co-authors on this work, and so he's also available for discussion. And we're also connected via Telegram. Good. So I just will flash an advertisement that there are still possibly it from Qubit postdocs and studentships available, including at UCL. Drop me an email if you are a general relativist or a quantum field theorist and are interested in applying. This is work which is available on the archive. There's an updated version. I can message you if you would like. It's joint work with Carlos Barriera, who's there with you now. Also Joan Kemps, Barbara Soda, and Zach Weller-Davies. The question I'm going to address in this talk is the question of, should we quantize space-time? I don't know that I have a terribly strong view on this. I guess I'm interested in just asking the question and seeing where it leads. So I want to just check. Let's imagine that space-time is not quantized and it's classical, and then see what the consequences are. I think it's somewhat natural maybe that we don't quantize space-time. You've been discussing at the conference issues like causal ordering. There's clearly a big difference between ordinary matter and ordinary quantum fields and space-time itself, since we need space-time itself to even define the quantum evolution equation to begin with. I don't think I need to say more at this particular conference about that. So effectively, I have no idea if space-time is actually classical, but let's ask the question. And what I will explain today is that despite a number of no-go theorems, space-time can actually be classical, gravity can be classical. And if we assume that it is, there's a number of interesting consequences that follow immediately. One of them is that it would automatically cause collapse of the wave function. Not quite a dynamical collapse model, but something that looks like it. It also would necessarily lead to information destruction, which is something I'm interested in from the point of view of the black hole information problem. And I believe that it's viable as a fundamental theory to have gravity being classical. But even if you don't believe it's fundamentally classical, then what I'm going to present today, I think, is an effect. You can view it as an interesting, effective theory. You can view it as a theory in which I could calculate in a consistent way the backreaction of quantum fields on space-time. So, for example, you could use it to calculate the backreaction in the classical limit on space-time during Hawking radiation or inflation. And the previous methods are somewhat pathological, so this provides a consistent way to do that. It's also, I think, especially for people who are interested in canonical quantization, it's especially interesting, I think, as a sandbox, a little toy theory, then, if you want to regard it as that, in which you can, in which many of the conceptual difficulties in quantum gravity can be studied in a much simpler theory. Good. So I hope those motivations are clear. I can't really see the audience, but if anyone has a question, then if you for one clarification, you can put up your hand, and I think someone can.
I don't mind. I'm here. So Jonathan.
Oh, is someone? Yeah.
Well, since you asked a question, since you just said that, you said I believe that a viable fundamental theory, it could be classical gravity and quantum mechanics. In the 70s and 80s, there was a huge discussion about that with a lot of literature on that, and a lot of argument were put forward, and the entire community convinced itself of the contrary. So what was wrong in the argument of the time?
Yeah, so I will go through what was wrong with those arguments. So there is, as you say, there's a huge literature, I think dating back to Feynman in the 70s, all the way up to recent work by Vladko Vedrel and collaborators, and so I will discuss those, what the loophole is. And in fact, most of my talk will be, I think, discussing that loophole. Is it right?
I look forward.
Yeah.
I don't know. Right.
Also, okay, good. So so as I said, one of the if you assume that gravity is classical, then you automatically get collapse of the wave function or the emergence of classicality. Effectively, if you have quantum systems interacting with classical systems, then classicality infects the quantum system, and so you have kind of collapse of the wave function that way. That kind of an idea has been discussed previously by Holland Reginato, although what happens in this theory is different to that. It's also a different kind of mechanism and for a different reason than Diyoshi Penrose, who also conjectured that maybe gravity has to do with collapse of the wave function, although for very different reasons. So one thing I like about this is you just assume gravity is classical and you get collapse of the wave function. The second reason I like this notion of assuming gravity is classical is that you automatically require information destruction. Now I like this. Almost every, I'm in the It from Qubit collaboration. Most of them are string theorists, and everyone hates information destruction. But I personally think that it's not so bad. We know from the black hole information problem, and in particular the AMPS version, which is that either we have to sacrifice. Can you see my cursor if I do this?
No. It doesn't.
Oh, you can.
Well, we see a cursor, but it's not moving.
That's mine.
All right, so maybe let me know if, okay, I'll try and be a bit more descriptive then. Well, that's funny. Okay, so
I think that's an option on your side to share the cursor too. I don't know if you can find that.
Right, all right. I'm not quite sure. Let's see if I do this. What do you see now? Do you see all my slides or something?
All your slides.
Yes.
All my slides, okay. All right.
Not his cursor.
I'm going to, maybe it's worthwhile to see my cursor. I'm just going to stop sharing the screen for a moment and switch screens, if that's okay. Apologies for this. Okay. And now you can see yourselves, is that right?
Yes. Yeah.
Great. And you can see me starting the first slideshow.
Yes.
Okay.
And now can you see my cursor?
No.
No. Okay. All right. Well, it'll be have to be. Okay. So I'll try and be descriptive of where I'm looking at. So the AMPS paradox effectively tells us. And sorry, can I ask now how much time? Because we started a bit late. How much time I have?
So we started at 4:37.
Okay.
So it's 40 minutes altogether.
Okay.
Plus
All right. So roughly, I should stop at around 7 past the hour.
Ideally, I mean, yeah.
Okay. Ideally for questions.
Yeah.
All right. Good. So the AMPS paradox, or apparent paradox, tells us that if we either have to give up, we either have to have information destruction, or we need to give up the equivalence principle, or low energy effective field theory. That's what I'm pointing to, the AMPS on the left horn of the bull. On the other hand, if we want information destruction, then there's a paper by Banks, Peshkin, and Susskind in '84, which tells us that we have to give up locality or energy conservation. So if we have information destruction, there's also going to be problems. Effectively, the black hole information problem tells us that we have to give up something that we cherish. Equivalence principle, effective field theory,
Jonathan,
linearity, or our dignity. Yes?
Jonathan, there is also another hypothesis there, which is some sort of holographic hypothesis, which is not one of those. So you can keep all those and give up something else. I mean, your string theory friends don't like it because they like ADF-CFT, but there is an extra hypothesis there, very strong, that the number of internal states of the black holes diminish, like, depending on the area. So you can keep all that and not have.
You mean if I believe in black hole remnants, you mean?
Yes.
Yeah. Race.
Yeah, okay, so a remnant is a possible solution to the black hole information problem, but I think it has difficulties as well. So there's difficulties in terms of, well, getting information out of such a small area, coupling to the remnant, and what that does for transition amplitudes, things like that.
Which is an holographic hypothesis, which is not one of those.
No, I don't think it's just the holographic hypothesis. I think that there's more than that. If you believe in remnants, then they can be created in processes.
No. This were all argument of the 70s. There's literature out of that. Those arguments don't hold.
So I'm aware. Okay, so I don't disagree that there are
banks of gatings of the time. There's literature out of that.
Yeah, I'm aware. So it's true that I could have long-lived black hole remnants. Whether that's in some sense that's the same thing as information destruction in a lot of for all points of view. From any point of view, there are issues with remnants in terms of how they couple. You can get rid of that by having coupling constants, which get reduced as the number of states they're coupling to increases. But whether that to me is not a very attractive solution, to have coupling constants which can be made, which just keep dropping as you drop the number of states. Let's not have a huge argument about the black hole information problem, because we
right, but don't make statements.
Let's just continue the talk, because I don't think it's that important for what comes afterwards, and maybe let's just let it finish the talk now.
Yeah, I'm happy to in the coffee break debate the black hole information problem, but I think most people would agree that that there are issues no matter where you turn, and difficulties, and I don't think anyone has a great solution at the moment. So in some sense, you can say that there are no-go theorems which tell you can't have information destruction. I wouldn't call them no-go theorems. Maybe they're strong arguments. One of them is this argument by Banks, Peshkin, and Susskind that if you have information destruction, you have to give up either locality or energy conservation. Another strong one is due to Coleman, which says that if you have information destruction, I can always imagine that the total theory is pure, the church of the larger Hilbert space, and if I do that, then we see that information destruction is just like having coupling constants which we don't yet know the value of, and once we learn the value, then we will not have information destruction anymore. What is nice is that these various no-go theorems in fact annihilate each other. I think I can't see always who's talking and recognize names, but I think it was Carlo who was talking about these no-go theorems about classical gravity. What we find is that classical gravity becomes possible because there is information destruction, and so those no-go theorems get annihilated, and that information destruction is possible because it's via classical gravity. So the various no-go theorems in terms of classical gravity and in terms of information destruction in fact annihilate each other. So for the rest of the talk, what I'll be, the program is that I'll first discuss the question of can we couple quantum and classical systems. I will then talk a little bit about what is the general form of this dynamics, and I'm not sure that I'll have a lot of time to discuss the specifics of it, but I'm happy to chat about that afterwards over coffee, and most of this is contained in the paper and in a forthcoming series of papers which are being prepared. Good. So let's ask the question, what kind of dynamics could be allowed? What do we mean by a system which has classical dynamics combined with quantum dynamics? And the first thing we need to think about is, what is the state space? What does states look like? And the hybrid state space, we have a Hilbert space, so we have a quantum system, for example, a spin qubit. And at each point, we have a Hilbert space at each point in phase space. So we can imagine that we have a density matrix for the qubit, so it's a 2x2 matrix. But also there's classical degrees of freedom. For example, a phase space, it doesn't have to be a phase space, but we have it's in a phase space. So you have, in some sense, a 2x2 matrix for the spin of a qubit, which now depends on degrees of freedom in the classical phase space. So here, in the middle of the slide, you can see we have the hybrid qubit, which has a classical Q and P, but it also has a matrix form. Is that clear? Okay. And before I get to the discussion of how we get around all these no-go theorems that I think it was Carla that was talking about at the beginning, and get around this debate that happened, what I will do is I will just show you the kind of evolution that we can have. And so those of you who are familiar with Lindblad equations will instantly recognize this. So here I have a qubit which is coupled to a external force, like a Stern-Gerlach. So depending on whether this qubit has a 0 or 1, it will go in a different direction. So let's I'm going to ignore the deterministic part. So the deterministic part of the master equation being its spin, being its Heisenberg evolution, its normal quantum evolution, and then also its pure classical evolution. I'm going to ignore that for the moment and just look at the coupling between the classical degrees of freedom and the quantum degrees of freedom. And if you look at this master equation, you can see, if you're not familiar with master equations, don't worry, I will come back to that. I'm just showing the slide for those who are familiar with such things. And you can see here in this master equation that when the qubit has a value of 1, then it starts to move in, it gets a jump in momentum, a kick in momentum of an amount given by tau beta. And if it has a spin 0, or if the qubit is a 0, then it will react and get a kick in the momentum in the opposite direction. And so this acts like a Stern-Gerlach and effectively measures the value of the qubit depending on what the momentum of the classical particle is. And this is a model amongst a number of other models that Carlo, who's at your conference, has studied quite extensively and who is able to do numerical simulations on this. And what we find is that the quantum state, this kind of an interaction, initially the quantum state is coherent, but after some time it collapses to the 0-1 state. It gets a discrete jump in momentum, and what's nice is that such a thing is probably experimentally measurable because there is a trade-off between the coherence rate and its, I say dispersion there, but I should have said diffusion. So this particle diffuses classically in momentum, or it decoheres, and there is a trade-off between those two rates. I could take questions about this. So about this master equation, if there are any short ones for clarification, but I will also get back to it.
I think we are okay.
Okay, then I'll move on. I will now address the question that was asked at the very beginning, which was, there was this huge debate in the 70s and starting in the 50s actually about whether we should quantize gravity, and the overwhelming answer is we needed to quantize gravity. And so there's been a series of discussions. I highly recommend reading the Chapel Hill Conference journal, which was transcribed by Cedar DeWitt. It's just a transcription of the arguments between Feynman and other researchers on why we have to quantize gravity. It's just very interesting historically. There's more modern versions of this thought experiment that I'm going to talk about due to Epley and Hanna, and there is a paper claiming that by Marletto and Vedral, saying that we not only have to quantize gravity, but even post-quantum theories of gravity. In other words, theories in which quantum theory is modified, such as this one, also need to treat the gravitational field in a quantum manner. So let's discuss now this no-go argument, let's call it, about why we have to quantize gravity. And it's effectively just this Stern-Gerlach experiment. We imagine that we have a heavy object like the moon, or just a heavy atom, and we're going to run an interference interference experiment with it. So we shoot it through these double slits, and it shows an interference fringe, or at least we think it should. And but because it's massive, it will create a different gravitational field, and of course also a different electromagnetic field, depending on whether it goes through the left slit or the right slit. And effectively, both the electromagnetic field and the gravitational field are measuring. You can think of them as measuring in which slit the particle went through. You end up getting an entangled state, here we have it, between whether a molecule went through the left slit or the right slit. So here's the moon going through the left on the bottom, or going through the right, and it gets entangled with the environment, which is either a quantum field or gravity on the left or the right. So the fields will be different, that it interacts with will be different depending on whether the molecule goes on the left or the right, and we get this entangled state. Does anyone know why the electromagnetic field doesn't cause the destruction of the interference pattern? So, because if we know which slit the particle went through, because we can measure the electromagnetic field from far away, then we should be able to determine which slit it went through, and we'll have no interference pattern. Does anyone know why the presence of the electromagnetic field and the fact that it's different depending on whether the molecule went through the left or the right, why that doesn't cause destruction of the, why doesn't that cause the interference pattern to be completely ruined?
I have an opinion which is probably not the same as yours. I would say none of them will cause, as long as you haven't measured the field, because once the particle gets on the same spot on the observation screen, the two states of the field will coincide, will factorize out, and that's why we do see interference in all our experiments so far. In spite of that.
But when it actually goes through the slit, do you think that it is maximally entangled with the electromagnetic field or the gravitational field?
I think this question has no meaning unless you complete the whole experiment. And so if there is a small probe particle, charged particle or massive particle, that will pick up the information which path you don't see interference. If there is nothing that couples to it, and you keep going with the interference, which is another experiment, then it will not be, it will be coherent.
But you can do the calculation, and with you can just use linearized electromagnets. You can compute the scalar product between the two photon states emitted and see that there's no decoherence here essentially. So it's not
right, exactly. So it's not a matter. You can measure the electromagnetic field or the gravitational field at any time. It's not a question of whether you actually measure it or not. It's more just a question of this fact, which is that the electromagnetic field, this EL, if the environment E left and E right, even though it's different depending on which slit the particle went through, it has a different state depending on whether the particle went through the left or the right slit. The point is that those two states are not orthogonal. Sorry, they're very similar. So if we look at if there overlap between so the electromagnetic field is different depending on whether the particle went on the left or right, but because it's a quantum state, because the electromagnetic field is quantum in nature, we can distinguish, no matter how many measurements we do far away from these slits or even close to these slits, we will not be able to determine whether the particle went on the left or the right, because those two states of the electromagnetic field are very similar, and they have, they're a little bit different, which leads to some decoherence, but they're mostly identical.
John,
They can't be distinguished.
can I say something? I mean, it's surely, as soon as you have a position which is different, you can come so close that you will see the difference in electron field. So, or in other words, even if they were orthogonal, as long as we are not talking about radiation, which goes away and you can catch the radiation and find the rich path information, even if they were orthogonal, the static field, there will be no interference if you close the interference path without having a test particle.
Don't forget though that the changes you make to the electromagnetic field are going to be, I guess I'm talking about the far field here. If you look at the field, these things I could measure far from the two slits. I can even get very close if these particles are trapped. There's a lot of these measurements I could do, which I could measure after the particle interferes. So if I were to move the screen closer to the slits, then I can record the interference pattern and then measure the electromagnetic field, and I would still see interference. And the key thing is that the electromagnetic field is different, but the two states are non-orthogonal. And the argument for why we have to quantize gravity is that for a classical states, so if the gravitational field is classical, then the gravitational field cannot be different depending on whether the particle went on the left or the right. If the gravitational field is different depending on whether the particle went through the left slit or the right slit, then classical states have to be orthogonal if they're different. So that is the argument about why we should quantize gravity. There's various shades of this argument, various versions of this argument, but in essence, that's the argument, that if we couple particles to the gravitational field and the gravitational field is classical, then we would automatically have to collapse the wave function right away, because we can distinguish the gravitational field exactly, we can measure it perfectly, it's classical, and so we could determine by measuring the gravitational field exactly which slit this particle went through. So here we have this LIGO, we have a gravity wave detector, gravity is classical, we can measure the gravitational field E left or E right to arbitrary accuracy and determine exactly which slit this particle went through.
I have a question. If that's the case, do you take this as experimental evidence that gravity is quantized?
That is the argument about, that was an argument of why we have to quantize gravity. So I think people were taking this as experimental evidence that gravity is quantum. And
do
I
you
guess
take
the
it
argument
as
of Feynman and Aronoff.
Do you think we have empirical evidence that gravity is quantized?
No, I wouldn't be giving this talk if I thought that. So the question is, what is the loophole around this experiment? Why does this experiment not actually test whether gravity is quantum or not?
Okay, thanks.
So I guess the question is why. So this statement that two classical states cannot be different and non-orthogonal. What's the loophole to the statement? And the answer is that two classical states can be different and non-orthogonal if they are not just pure classical states, i.e. particular classical states, but if they are distributions. So if the molecule goes on the left and the gravitational field has a probability distribution, depending on whether the molecule went to the left, and if the molecule went to the right, the gravitational field has a different classical probability distribution, then those classical probability distributions can be different and non-orthogonal. And so this means if the coupling is stochastic, then classical gravity does not have to be incompatible with quantum theory. So that is the loophole around most of these thought experiments that told us, or even experiments as people thought of them, which told us that gravity had to be quantized. Is that argument clear?
So are you saying, not very well, so are you saying that if I take a mass and I put it in a superposition of two different positions, then the corresponding gravitational field is sort of randomly sometimes determined by the left, sometimes determined by the right? Is that what the picture of the world?
That's right. So you can imagine that I start off with a mass in a particular location. I try and put it in superposition, and when I move it to put it in superposition, it will couple stochastically in a random array with the gravitational field. And so when I look at the gravitational field, because of the stochastic coupling, I sometimes am able to determine, I may get some information or some partial information about whether the particle is on the right, but I can't tell with certainty, and so the particle could still be in superposition.
No. Forget what you can tell. The actual gravitational field, which is classical.
That's right, and it's in a classical statistical mixture.
It just, sometimes it happened to be the Coulomb field of the right particle, sometimes happened to be the Coulomb field of the left particle. Is that your picture?
My picture is like this. So that if I look at here we go. So if I put in a superposition of the moon on the left and the right, then the gravitational field will look. There's one of many possible gravitational fields that could be associated with a particle on the left or the right, and it's stuck. So there's a distribution of configurations, of classical configurations, and I cannot tell them apart.
A distribution is a classical distribution, so it means that it is in one given state and we don't know in which one it is. And there aren't many possible.
No. We can tell which one it is. So we can tell which state the gravitational field is in because it's classical, so we can measure it with certainty. But based on that information, we are not able to determine whether the moon is on the left or the right.
Fine. Forget the argument. Forget Feynman argument. I just want to know what you think is happening. I take a mass, I split in two, and now you're saying that nature decides randomly whether there is a Newton field centered on the right or a Newton field centered on the left. Just sometimes one, sometimes the other.
And maybe particle is on one side and the gravitational field on the other.
Do you find this reasonable? And do you find this is...
No, but I'm saying that there is, so the state will look like this. This is what the state will look like. You can imagine here. So here's this hybrid state. So it'll be so normally we would imagine that the state just looks like a density matrix. So if we're not coupling to a classical field, we pretty much will have something which looks like a classical field. Well, pretty much something which looks like this. There is a particle will be described by a density matrix with a probability of being on the left, a probability of being on the right, and some off-diagonal elements here. And the value of the and those that will not depend on the value of the classical field.
But if I don't look at the
but here you have a classical gravitational field, and so the density matrix will depend on this classical gravitational field.
Yeah, so if I don't look at the particle, I only look at the gravitational field, I just come from test mass and see the acceleration, then I sort of randomly see sometimes one thing, sometimes this is all classical, but sometimes I see one, sometimes the other, independently of whether I'm going to measure the particle later. I mean, just...
Not quite independent, so there'll be some dependency on where the particle is later. but not enough to determine it. So yes, there will be different you measure it, and sometimes it'll sometimes have some values, sometimes other values. And I take it from your, I can't see the expression on your face, but I'm guessing it's slightly incredulous. Is that true?
That's very accurate.
Yes. And you are incredulous because you believe that information is preserved. So you don't believe that nature can have fundamental randomness.
I don't see any reason for inventing something new, different from quantum mechanics and the existence of the gravitational field that we have. I don't see why going into such strange phenomenology. I don't see any reason for going there. I don't see any indication in nature that one should do something totally new of this sort.
So how is quantizing gravity going for you at the moment?
The rest of the time for that.
I don't know. Send you a couple of books.
I'm not so like I said at the beginning, I'm agnostic on the idea whether space-time is classical or quantum. I'm a quantum information theorist by training, and I love quantum mechanics, and I want to quantize everything. And so like you, I think I would really like space-time to be quantum. I'm just merely exploring the consequence of whether it could be classical. And what I find is that it can, which I think is interesting. There's nothing, there's no inconsistency from taking it to be classical. And what I also find is that there are two nice byproducts and consequences. One is that it, in my view, solves the measurement problem to the extent that people feel there is one, and it leads to information destruction, which in my view is the best way we have out of the black hole information problem. So, people have very strong opinions on these matters. I don't. I just want to see where the evidence, I just want to explore the possibilities. And I think that what's happened until now is that everybody has explored, pretty much, except for people like Bill Unruh and Bob Wald, have pretty much only explored the one side of the, let's go back to our bull, have only explored one of the horns and are willing to give up a lot of things which I wouldn't be willing to give up. And I'm going to just throw myself on the other horn, and things might get messy. I don't doubt that they will, and I'll get a bit bloody, but I want to see how far it goes. Is that motivation clear? Okay, I can't see the expression now.
but I would suggest that maybe we just progress towards the conclusion of the talk. I mean, of course, there are many ideas that need to be discussed, but we cannot do it all during the talk.
Okay, good. So I will just very quickly now mention one more reason why people don't like to treat classically. It's to do with the fact that when people hear that gravity is classical, what most relativists and most quantum gravity people think about is the semi-classical Einstein equation, which is this equation here. The reason we should quantize gravity is because the left side of this equation is classical and the right side is quantum. So what do? Well, the first thing people tried is they just put expectation value around the quantum part, the T mu nu, and that is called the semi-classical Einstein equation, and it's pathological. It's what we use to compute the backreaction during black hole evaporation, but it has the following very obvious problem, which is that if I imagine, let's look at the left-hand panel here, I imagine that I flip a coin, and if the coin is heads, I put the planet on the left, and if the coin is right, is heads, sorry, I put the planet on the right. And now if I drop a test particle, what I would expect is that the particle goes towards the left planet or goes towards the right planet. But if I look at the semi-classical Einstein equation, then what actually it tells me, if I look at the stress energy tensor, is that half the there's half a planet on the left and half a planet on the right. And so what happens is that the test particle will drop down the middle, and the two planets will, the two half planets will be drawn towards the place that the other planet would have been had the coin been heads instead of tails. And that, of course, is pathological. And so semi-classical gravity, we can't have that. And so a lot of people also take this to be an argument about why we should quantize gravity. But I would say it's just an argument about why we shouldn't use the semi-classical Einstein equation, and because it's nonlinear. And the theory that I will propose is linear in the density matrix, and so it doesn't lead to these pathologies, and that makes it a viable, even an effective theory of quantum gravity. Of quantum fields coupled to, or I should just say, a good effective theory when we take the limit that the gravitational field is classical. So if we want to study the backreaction during evaporation of a black hole or cosmology, we shouldn't be using the semi-classical Einstein equation because it's pathological, but we can use this master equation that I'm going to present. Okay. So I'm going to try and go quickly. I guess I'm about to run out of time, but what I'll just say is, what is the general form of this dynamics? For those who are quantum information theorists, you will love this, I think, in the sense that you now can go through quantum information theory and relearn all the classics like the Krauss representation theorem or the uniqueness of the Lindblad equation, and now you will see that we can effectively, get dynamics which has a similar form as both classical and quantum dynamics, but somehow combines them too. So we are going to demand that our theory be linear. It must preserve the state space. So if we have a quantum classical state, it must remain a quantum classical state. That means that if it's a positive density matrix, it must stay positive. And if it has trace one, and by trace, if the total probability needs to be, the total probability needs to be conserved, which means that if we take the trace and integrate over the classical degrees of freedom, that must give us 1. So that's there's a new, a generalization of the Krauss representation theorem. And so what we find is that we can have this kind of quantum dynamics at the top. This is what classical dynamics looks like in the middle, and then the classical quantum dynamics looks kind of like a combination of both. Likewise, we can go to a master equation if we demand that it's Markovian, there's no fundamental memory. And so what we get is, on the top you have the Lindblad equation, in the middle you have the classical dynamics, Markovian dynamics, which is called the Pauli rate equation, and at the bottom you have something which combines both of them. It was actually known in '93 and has been studied since. And so the contribution here is effectively to find a way, so this is a very general form of the dynamics which doesn't let you couple it to an actual dynamical system, but what I show is that there's a way to couple it to an actual dynamical system so that you reproduce you reproduce your ordinary classical dynamics in the limit, and in particular you get general relativity in the classical limit, and I will go to my conclusion now. Good. So we can apply this to general relativity. It's fairly complicated because you have to deal with the constraints and gauge invariance, and it's a field rather than just say a qubit. But you can look at quantum fields influencing classical spacetime and get an ADM type master equation. And you find you evade the usual no-go theorems, and including the BPS argument. And I will just end like this. The conclusion is this. So this is just the top messages. We can assume, just for the point of argument's sake, let's just assume that spacetime is classical and remains classical. It necessarily causes quantum systems to become classical, so it helps with the measurement problem. It necessarily leads to information destruction, which I like because I find that's the best way out of the black hole information problem. It turns out you get discrete and stochastic classical jumps, so decoherence versus diffusion, and Carlo has studied that in great detail. You can chat with him about that. And so what we find is that we can have classical gravity, we can regard it as either fundamental or as the classical limit of quantum gravity. And so it provides a good effective theory for calculations and an interesting sandbox in which to study many of the conceptual difficulties that we have with trying to quantize gravity. And with that, I'd like to thank you for your attention.
The time and the lively debate you have during the talk, I would give time for one last question, if there is one, of course. Yes.
If
please.
there are no questions, if I'm sure you know your colleagues, if Sugato Bose and Chiara Marletto and Blanco experiment is going to be performed, assuming that it's performed and assuming that it all works and it gives a positive answer, would that rule this hypothesis out or would it not?
Would what, sorry, would it?
Would it rule out this?
Yes, it would rule it out as a fundamental theory. It still can mean that it's an effective theory, but it would certainly rule it out. And I'm happy to take a bet with you if you would like.
Yeah.
How much?
Bottle of wine?
Sounds good.
Great. So let's thank Jonathan again.